So in this video, we'll discuss linear momentum. So what is momentum, you may ask? It's important to understand that momentum can be denoted as P, and momentum is a motion quantity, and it's similar to your velocity and your acceleration. However, your change in momentum, right? So change is denoted as like your final momentum minus your initial momentum can be denoted as delta of your momentum. And the change in momentum is also known as your impulse. An impulse is denoted as J. Not to get confused with joules. Joules is a unit of measurement for energy. Impulse refers to the change in momentum. And this connects back to Newton's second law, which states that change momentum, your impulse, is proportional to time. Mm. So now that we have an idea of what momentum is and how your impulse is calculated, which is just your final minus your initial momentum, um, and how time and momentum are proportional to one another according to Newton's second law, we can take a look at some examples regarding conservation of momentum. So this problem states, in a railroad yard, a train is being assembled. An empty boxcar coasting at 3 meters per second strikes a loaded car that is stationary, and the cars couple together. Each of the boxcart has a mass of 9,000 kilograms when empty, and the loaded cart contains 55,000 kilograms of lumber. So the first thing we need to do is write a conservation momentum expression. So we know that the conservation momentum states that our initial momentum is going to be equal to our final momentum. And the way you calculate for momentum is your mass times your velocity. That is what momentum is equal to. So we know that this, or our initial momentum, is going to be the momentum before before the cars couple together. And because we know that the empty boxcar is coasting at 3 meters per second and that the loaded car is stationary, we know that the loaded car is at rest. So before any collision happens, they're independent within each other. One doesn't affect the other. So we can rewrite our initial momentum as two separate mass times velocities. So we can do mass times velocity of the boxcar, which will denote as sub b, and I for initial, plus mv. We'll do c for loaded car, and then again I for initial, is going to be equal to the total final momentum. So total, denote this by f. Okay. Because we know our loaded cart goes to 0 meters per second, we don't need to know what the mass of the loaded cart is. Like, even though we're given it, we don't necessarily need to know it for the initial portion of this equation. Because regardless, our velocity is 0, so we don't have any momentum. So this just goes to 0. So now we're just left with mv b sub b I is equal to mv total of our final. Right? So now we have a written conservation momentum expression. And the question asks us to find the speed of the coupled cars. So once they're coupled, what is the speed? So we're trying to get the final speed. So one way we can do this is by dividing the mass of the total system to both sides. So we're given the mass is 9,000 kilograms of the box cart and 55,000 kilograms of the loaded car. So we can simply add these to get the total mass. And then this is simply going to be 64,000 kilograms. This is going to be 64,000 kilograms over the mass of the box cart, which we said was 9,000 kilograms, times our initial velocity of the box cart, which is 3 meters per second. And we can plug this into a calculator. Which would give us a final velocity, or a final total velocity of about 0.4218 meters per second. And that's the answer to this question. Let's take a look at a different example. Okay, this example says an astronaut of mass 80 kilograms. So the astronaut, we'll say A for astronaut, is equal to 80 kilograms. Carries an empty oxygen tank of mass 10 kilograms. So we'll say M sub T for the tank is 10 kilograms. By pushing the tank away with a speed of 2 meters per second, the astronaut recoils in the opposite direction. And in this specific problem, we're told to find the speed with which the astronaut moves off into space. So initially, the astronaut and the empty oxygen tank have no velocity. It's only once the astronaut pushes the tank away from himself that pushes himself away with the speed of 20 meters per, or sorry, not 20, 2 meters per second, that the astronaut starts to move. So we know that our final velocity for the tank is going to be 2 meters per second because initially both the astronaut and the empty oxygen tank are not at any movement. They're not moving. So we know our initial momentum is going to be zero. And it's also important to note that the units for momentum is simply newtons times seconds. Um, so now that we know that our initial momentum is going to be set equal to zero, we can write a conservation of momentum expression based on what we already know. So we know that our initial momentum, right? So P, our initial momentum is going to be equal to our final momentum, but we know our initial momentum is going to be equal to zero, so we can just set our final momentum equal to zero. And our final momentum, since this doesn't require the connection or the connection of two items, however, they're separating because the astronaut is throwing the oxygen tank away from him, rather than the previous example where the two objects collided and they joined within each other. In this example, they're separating. So we're not going to combine them into a total or a single momentum. Rather, we'll have mv sub, we can say A for the astronaut, or and then F for final. So this is the final astronaut's momentum plus the oxygen tanks. We'll denote that by sub T of F for final. And we know the masses, so we can plug in the known mass. So we know our astronaut weighs 80 kilograms. However, we don't know the astronaut's final velocity. But we do know the oxygen tank's mass, which was 10 kilograms. And we do know the final velocity of the oxygen tank, which was 2 meters per second. And then the question is asking us to solve for the final velocity of the astronaut. So we can simply separate for v here. So we know 10 times 2 is going to be 20 kilograms times meters per second. And then this is going to be 80 kilograms times my velocity plus 0. We can subtract the 20 to both sides, which will leave us with negative 20 kilograms of times m over s equals 80 kilograms over, or times the astronaut's final velocity. And we can Divide both sides by 80 kilograms. 80 kilograms. Leaving us with negative 1 over 4 meters per second is equal to the astronaut's final velocity. And the negative sign is important in this specific situation because we have to understand that the prompt specific told us that the astronaut recoils in the opposite direction. So this negative sign is necessary for the specific scenario. Let's take a look at one final example. So this question states, a 50 kilogram cart is moving across a frictionless floor at 2 meters per second. A 70 kilogram boy riding in the cart jumps off so that he hits the floor with zero velocity. Okay, so let's write down the known variables. So we know initially, before any collision occurs within this problem, we know that the cart, so we'll say m sub c, is equal to 50 kilograms, because that's what we were told. And we know that the boy, which will represent as m sub b, is equal to 70 kilograms. And that the cart is moving on a frictionless floor, so we don't have to worry about friction or force acting against our direction. But we know that our initial velocity for the cart, which we'll denote as v sub c, and an I for initial, is 2 meters per second. However, we're not told about the boy's initial velocity, but we are told about the boy's final velocity when he jumps off the cart, which will represent as v for velocity sub of the boy final is going to be equal to 0 meters per second. And we know that because we're told that he jumps off with a zero velocity. So from this situation, uh, we're asked how large of an impulse did the boy give to the cart. So this is a bit of a different question than what we're used to because we were previously just dealing with momentum. But now we're going to deal with the change in momentum because we're asked about the impulse. So recall that our impulse is denoted by J, and it's equal to delta, or change of my momentum, which is also easier known as my final momentum, or P sub F minus P sub I for my initial. And we're finding how large of an impulse did the boy give to the cart. So we're only focusing on the boy's momentum. Okay. So now that we have written a conservation of momentum expression, we can plug in our known values. So we know that uh, our impulse is going to be equal to our change in momentum. However, we're not going to write it out as this, but rather we're going to write out all our variables, which is going to be m v times, or sub b for boy, final minus m v sub b I. So my final momentum minus my initial momentum. Okay, the key thing to note is that our final, right, our final momentum, regardless of the mass, this will always come out to zero because anything times zero is just going to be zero. So because we know our final velocity is zero, this by default, regardless of the mass, is it has to be zero. So now we know that our impulse is equal to our negative initial momentum of the boy. And now we can plug in our known values. So we know that our the mass of the boy is 70 kilograms. And we know because the boy is the and because we know that the boy is riding the cart, we know that he has to go at the same velocity as the cart because because the prompt told us that the cart is moving across a frictionless floor at 7 meters per second, and that the boy is riding the cart. So therefore, the boy also has to be going 2 meters per second. So we know that our velocity for the boy is 2 meters per second, and therefore our change in momentum is negative 140 kilograms times meters per second. And that's the answer to how large of an impulse the boy gave to the cart. Now, the other question asked, what was the velocity of the cart after the boy jumped? So in this particular instance, we can combine the system as one final object. And what I mean by this is, if we scroll down, what I mean by this is that we can rewrite this as our initial momentum plus our final momentum is going to be equal to our total momentum, or our total final momentum. And we can do this by adding the masses together. So again, we were told that the cart weighted 50 kilograms and that the boy weighted 70. So this leaves us with of a total mass of 120 kilograms. Again, that's just adding the mass of the cart and the boy. But before we plug in these values, let's put this in terms of the variables that we are given. So we can rewrite this as mv sub um, sub sorry sub c, an initial, plus um, we can write the we can rewrite the this for the boy, which would be mv of the boy, and final is going to be equal to mv total. Okay. And since we want to know the total velocity of the car after the boy jumped, we know the total. We know the value for the final velocity because the car will still continue to go at 2 meters per second, but we just don't know the velocity of the boy after the boy jumped. And what gets momentum a bit confusing is that you have to understand the different time frames into which you're looking at, because in this specific scenario we're no longer looking at the instance from the car from the car going and then the boy jumping on the cart, but now we're going, rather than looking at that time frame, now we're going from the boy riding the cart to the boy jumping off. It's a bit trivial, but once you understand the context into which you're looking into, momentum becomes a lot more understandable. So let's proceed. So we know the mass of the cart is 50 kilograms because again that's what we were told, and then we're solving for the velocity of the cart. So we don't know this value, but we do know that the boy has to jump. The boy jumps, so therefore this has to go to zero because remember we were told that he jumps, and once he jumps, his velocity is zero. So regardless of the mass, it's just zero. So this just goes to zero. It's going to be equal to the total, and we calculated the total mass, which was 120 kilograms. And again, the car is still going to continue to go in 2 meters per second. So this again is 2 meters per second. Because remember, we were told that the car moves across a frictionless floor at 2 meters per second. So now, to solve for our cart's velocity, we can simply divide by 50 kilograms because we divide the mass out and divide the mass out here too. And this would leave us with our cart's velocity, right? If we just put that into a calculator, we should get uh, 4.8 meters per second. There is one slight mistake. So again, regarding the time frame into which you're looking at, what may have confused you up here is final. This is meant to be your final, not your initial plus your final. No, that doesn't make sense. Again, we're looking at the final momentum is going to be equal to your total final momentum. Again, it's a bit intuitive and a bit abstract because you're not seeing like an actual video, but rather you're given the context and have to observe it from the given information. Um, but yeah, that's linear momentum. Understand that your impulse is your change in momentum, and your momentum is proportional to your time, and you can calculate your momentum by multiplying the mass of the object times the velocity of the object. Understand the context whether you're looking at elastic or inelastic momentum. Um, there's another video that I have uploaded where I go more into detail about elastic and inelastic momentum. Just understand elastic means that energy is conserved, while inelastic, you can think of in as not, so energy is not conserved. Depending on the type of momentum, will depend if you can combine your velocities or if you cannot combine your velocities. And that's all.